In previous lectures regarding Laplace equation in spherical polar coordinates, we have seen the solution of Laplace equation in spherical polar coordinates in two cases. The first one was its solution in case of when potential was spherically symmetric, and the second case was in fact general case in which we have solved Laplace equation in 3 dimensions. After knowing these facts, now I am today giving you 2 important examples, or you may say 2 important problems, which are solved on the basis of by the use of Laplace equation. Although such problems find its solution in different methods, as we have studied in the topic Gauss law, but here our limitation is we will solve such problems by the use of Laplace equation, particularly in spherical polar coordinates. The first example which I have taken is the potential on the surface of a sphere of radius A is given by phi naught equal to a sine square theta by 2, where theta is the polar angle, and we have to solve this problem by using Laplace equation, and I have to find the potential at a point inside the sphere. Let us see this. Suppose this is a sphere of radius A. You see here in figure that the radius of the sphere is A, and I have taken the polar axis, that is Z axis, and P is a point whose distance from the center of the sphere is R, and this point is inside the sphere. The problem says we have to find the potential at this point, and in the problem it is given that potential at any point on the surface whose polar angle is theta is equal to a sine square theta by 2. Let us see how we will solve such problems. See the problem and think seriously. Here potential is given on the surface of the sphere, and the problem has in fact azimuthal symmetry, because phi is given in terms of theta, so the problem has azimuthal symmetry. And as you know, in case of azimuthal symmetry, what is the solution of Laplace equation? In this case, the potential is independent of the third coordinate phi due to azimuthal symmetry. Azimuthal symmetry here I am writing symbol phi for potential. This phi is independent of a small phi, that is the third coordinate, and if phi is independent of this small phi, the problem becomes 2-dimensional. Phi will depend only on r and theta. And you have seen in previous lecture what is the solution of Laplace equation in this case of azimuthal symmetry. I am just going to write that solution as you have seen such a solution in previous lecture. So potential at a point P inside the sphere, inside the sphere satisfies Laplace equation. For simplicity, I write Laplace equation as LE, and its solution is given as. Remember, what is solution of Laplace equation in case of azimuthal symmetry? This is simply phi of r theta is equal to summation over L equal to 0 to infinity AL r to the power L plus BL upon r to the power L plus 1 into PL of cos theta. PL of cos theta. Remember, in this equation, PL of cos theta is what? In fact, it is Legender's polynomials. As you have seen, in case of azimuthal symmetry, m is 0, and when m is 0, then the associated Legender polynomial becomes Legender polynomials. Now see the situation in the problem. As we know, inside the sphere, everywhere potential should be finite. As it should be finite everywhere, so it must be finite even at the center of the sphere. But what you see here, at the center, r will be equal to 0, and if we put r equal to 0 in this solution, particularly in second term of the solution 1, if we put r equal to 0, you see when you will divide BL with 0, you will get undefined result. It means phi will be undefined. At the center, r equal to 0, and this implies phi at 0 theta will be equal to infinity. But remember, potential cannot be undefined anywhere inside the sphere. It must be finite. So how we will overcome this difficulty? This will overcome only when this term should not be included in our solution, and for this the constant BL must be equal to 0. Potential to be finite everywhere for r less than 1, that is inside the sphere, r less than 1, BL should be equal to 0. And so, if BL is 0, what will be our solution? Equation 1 then becomes what? So, our solution will become phi of r theta equal to summation over L equal to 0 to infinity AL r to the power L into PL of cos theta. This will be our solution. This is in fact you may say the valid solution of Laplace equation in this condition. Now, in the problem we have given the value of phi at the surface of the sphere, and at the surface you know at the surface what is the value of r? It is simply equal to a, which is radius of the sphere. So when we write the expression for phi at the surface, we must replace r in our equation by a. Hence, phi at a theta. This is in fact potential at the surface, which is given as phi naught in the problem, and this will be equal to what? In accordance with equation 2, we may write it as summation L equal to 0 to infinity AL, a to the power L, r is replaced by a, into PL of cos theta. This is potential at the surface. But we have given in our problem phi naught equal to a sine square theta by 2. So let us see. By the solution of Laplace equation, we find that the potential at the surface of the sphere is this much, and in the problem this potential is given as a sine square theta by 2. So we can equate these two equations. So let us equate these two equations. So we will have summation L equal to 0 to infinity AL, a to the power L, PL of cos theta, and this equal to a sine square theta by 2. Let us simplify this equation. Here expand this term in LHS by substituting the different values of L. As L runs from 0 to infinity, Let us expand it. This will be what? A naught when we put L equal to 0, A to the power 0, P0 of cos theta plus, now put L equal to 1, A1, A to the power 1, P1 of cos theta plus, similarly we take L equal to 2, so A2, A to the power 2, P2 of cos theta plus so on, and this will be equal to A sin square theta by 2. From trigonometry we know sin square theta by 2 is simply 1 minus cos theta divided by 2. This is a simple formula which you have seen in trigonometry. Now, this RHS may be written as A by 2 into 1 minus A by 2 into cos theta. Remember, I have discussed some important values of Legendre polynomials. We have seen P0 of x, which is in fact P0 of cos theta, x represents cos theta, this equal to what? This is 1. And P1 of x, which is in fact P1 of cos theta, this is equal to x, and x means this is equal to x, and this is cos theta. This is x, and this means cos theta. So let us substitute these values here. This is equal to A by 2 P0 of cos theta and minus A by 2 P1 of cos theta. Let us see. In LHS there are in fact infinite number of terms, and in RHS there is only two terms. So now compare the LHS and RHS term by term. When we will compare LHS and RHS, we find that the coefficient of P naught cos theta in RHS is A by 2, and in LHS it is simply A naught, because A to the power 0 is in fact 1. So now we compare the coefficients of different order of Legendre polynomial in LHS and RHS. Comparing the coefficients of PL of cos theta. PL of cos theta. We compare the coefficients of different order of PL of cos theta in LHS and RHS. What we will find? We will find that A naught is equal to A by 2. A naught is equal to A by 2. And A1 into A. See here, A to the power 1. So this is simply A1A. This will be equal to minus A by 2. See here. This is equal to minus A by 2. And from here what we get? A1 is equal to minus A over 2A. A over 2A. One thing, see here, in RHS there is no other terms, but in LHS we have the terms containing the higher order of Legendre polynomials. It means all the higher order of Legendre polynomials, when L is greater than 1, vanishes. All are 0. And we say here AL is equal to 0. This is 0 for L greater than 1. So A2, A3, A4 and so on, all will be 0. Now we can find the potential at the internal point of the sphere. We have to find potential at this point, which is inside the sphere. For this, in fact, we see from equation 2. So from equation 2, in general, potential at r theta, remember r is less than a because the point is internal point. This will be what? Let us expand the expression in RHS of equation 2. This will be simply A naught P naught of cos theta plus A1 R P1 of cos theta. Remember, we will not expand further because all the other coefficients, that is A2, A3, A4, so on, are 0. So this will be our result. Now substitute the value of A0 and A1, which I have find out in above calculation. You see A0 is in fact A over 2. So this will be A over 2. And P0 cos theta, you know it is in fact 1. So this is simply A over 2. And A1. A1 is equal to what? This is minus A over 2A. So A1 is replaced by A over 2A with negative sign. and into r p1 of cos theta. You know p1 of x or p1 of cos theta is in fact equal to x, and x is written as cos theta, so this is cos theta. So finally we get the potential phi of r theta equal to what? Let us take a over 2 as a common factor. This will be 1 minus r over a into cos theta. In fact, this is our result. This is the expression for potential at an internal point of the sphere. Remember, this result is valid when r is less than a, because we have calculated the potential at a point which is inside the sphere. So you have seen it is very interesting to solve the problem by using the solution of Laplace equation in spherical polar coordinates. So it is a very useful, a very powerful mathematical tool to handle such problems. Now let us take another example. For convenience, I write down the problem using Laplace equation. Find the potential at any point due to a uniformly charged circular ring of radius say a, carrying a total charge Q. Let us see how we can solve this problem by the use of Laplace equation. In this problem, we have given a circular ring of radius A. See the figure. Remember one thing here, that whenever the situation is three-dimensional and we show a circle in a two-dimensional plane, but the situation is of 3D, we must show the circle as an ellipse. That will be correct. So I have shown in the figure the circular ring as an ellipse. Let us take the center of the ring as a origin and construct the three orthogonal coordinates x, y, z as you see in the figure. Now the problem says that this ring is uniformly charged. It means its linear charge density will be constant, and total charge on this ring is Q, and we have to find the potential at a point anywhere. Let us say at a point P at a distance r from the center of the ring. We let the polar angle is theta. It means the radius vector of point P, which is r, makes an angle theta with the azimuthal axis, that is z axis. Now we have to find potential at this very point by the use of Laplace equation. Here we also see the problem has azimuthal symmetry, and so due to azimuthal symmetry, why it is you say that the problem has azimuthal symmetry? Because symmetry about z axis of potential phi at any point outside the point is obvious, as about the z axis, if we consider the ring is in xy plane, the charge distribution is symmetric about z axis, and z axis is the azimuthal axis, so the problem finds azimuthal symmetry. And in this condition, in the case of azimuthal symmetry, what is the solution of Laplace equation you have just used in the previous problem too? So we will write the solution in this case of Laplace equation as in previous problem. So due to azimuthal symmetry, due to azimuthal symmetry, solution of Laplace equation in spherical polar coordinates. Spherical polar coordinates. What will be the solution? You have just used it in the previous problem. At any arbitrary point P, the potential function will be given as by the solution of Laplace equation as summation over L 0 to infinity AL into R to the power L plus BL over R to the power L plus 1 into PL of cos theta. This is in fact a solution of Laplace equation when azimuthal symmetry exists. Now let us see. In this problem, there will be in fact two cases. First one, I am going to consider that R is greater than A. That is, the point P lies at a point whose distance from the center of the ring is greater than a radius of the ring. So for R greater than A, when we consider R greater than A, it means we can take the value of R from A to infinity. It means you may say the case is A is less than R and this is less than infinity. It means we may take R equal to infinity. But see the above solution. When we will take R equal to infinity, if we take r equal to infinity and put that r equal to infinity in this expression. See, in first term, if you put r equal to infinity, the result will be infinity. So you can say, if we take r equal to infinity, then phi will be equal to infinity, which is impossible. This is impossible result because potential cannot be infinity at r equal to infinity. It is obvious. What you think that potential will be at infinity? In fact, when r will tend to infinity, in a strict sense of mathematics, we should not take r equal to infinity, but we should say r tends to infinity, then phi must tend to 0. This is our real physical situation. This is reality. And when this reality will come? This reality is possible only when this first term does not exist in our solution. Because if this term is not present, the result will be not infinity. And see the second term, if we put r equal to infinity, then definitely phi will become 0, because when you will divide VL with infinity, the result will be 0. So this is the real physical situation, and for this what you get? We get that AL must be 0. That is the first term should not be in the solution, and it will be not in the solution only when AL will be 0. So for the fulfillment of this condition, we must have AL equal to 0. So we find AL should be equal to 0. Now, as AL should be 0, we have discussed in detail. So now what will be the solution of Laplace equation? It means what will be the form of equation 1 in a real situation. You may see we must take AL equal to 0, and the remaining factor will be the solution of Laplace equation. So our equation 1 becomes phi of r theta will be equal to what? This will be L 0 to infinity BL divided by r to the power L plus 1 PL of cos theta. This will be our solution, in fact, in this situation. Now see the figure. I have shown in the figure. We see, let us consider a point on the polar axis, that is z axis, and the distance of this point we take equal to r, in fact, which is the distance of our test point, and from any point on the periphery of this ring, the distance of this point will be what? As it is A and it is equal to R. We have taken arbitrarily a point whose distance from the center of the ring is R, and you see here from the geometry that distance of this point from any point on the periphery or on the circumference of this ring will be simply a square plus r square square root. Now, as all the points on the ring are equidistant from this point, this is the distance of any point. So, if we want to find the potential at this point, then we can simply apply the general principle or Coulomb's law to find the potential. One thing, see here, when you take your test point on the azimuthal axis, that is z axis, theta will be what? Theta will become 0. So, if you take any point on z axis, for all those points r will be different, but theta will have a fixed value that is equal to 0. So let us define the potential at this point. We know if we consider a small element on this ring and find the potential at this point. Potential, let us say this point is P dashed, potential at P dashed due to a small element of the ring, a small element of the ring. Let us say this potential is d phi. This will be what? We know from the basic definition of potential, this will be 1 over 4 pi epsilon naught dq by a square plus r square square root. This is potential due to a small element which we have selected at anywhere on this ring. So now we can define the potential at that point due to the charge distributed on the whole ring. So potential at R0, see this is in fact value of theta, potential at R0 due to the ring, charge, you may say charge ring or the charge distributed on the ring. This potential we denote by phi of R0, phi of R0. And what will be this? This will be simply 1 over 4 pi epsilon naught into 1 over root over a square plus r square into integral of dq. Why integral? Because charge is continuously distributed on this ring. So instead of summation we take integration, and this will be equal to 1 over 4 pi epsilon naught q divided by a square plus r square whole to the power half. Now we expand the RHS of this equation, and remembering one thing, that in this case we have considered that R is greater than A. Taking this fact in our mind, we will expand this term. this is equal to 1 over 4 pi epsilon naught into r. We have taken the term r square as a common factor, as it is inside the square root, so outside of the square root it will be simply r, and the remaining term will be what? This will be 1 plus a square over r square and whole to the power half. So this is 1 over 4 pi epsilon naught into r. Let us take this term in numerator. This will be 1 plus a square over r square and whole to the power minus half. This will be minus half. Let us see. We can expand this by binomial expansion, and when we expand it by binomial expansion, what will be our result? The result will be simply remember one thing, we have dropped q, so here will be in fact q. And now expand this expression by binomial expansion. What we will get? This is in the form of, in fact, 1 plus x to the power minus n. 1 plus x to the power minus n. So let us expand it. This will be q over 4 pi epsilon naught into r into 1 plus x to the power minus n. Using the formula for this expansion, we will expand the term. You will get simply 1 minus a square over 2r square, 1 minus nx, plus 3a4 over 8r4 minus so on. Let us say this is equation number 3. So we have defined the potential at a point which is at a distance r on the azimuthal axis, that is z axis. That is a point for which theta is equal to 0. I have defined the potential. Now, using the solution of Laplace equation, we will again define the same potential by the solution of Laplace equation in the light of equation 2. So from 2, what we will get for the same potential from equation 2? Phi of r0. Let us see. This equation will be what? Summation L0 to infinity BL over r to the power L plus 1 and PL cos theta. This will be cos 0 and cos 0 is 1. So here will be PL of 1. Remember one thing, PL of 1 is equal to 1. For any value of L, PL of 1 will be equal to 1. So taking this value of PL of 1 equal to 1, if we will expand, what we will get? We will get simply, let us put L equal to 0. This will be B naught over R to the power 0 plus 1, that is R, that is 1. So this is B naught over R plus, now put L equal to 1. So the second term will be B1 over R to the power 2 plus B3 R cube and so on. Let us say this is equation number 4. We have written the potential in terms of solution of Laplace equation in present situation, and independently in equation 3 we have find the same potential. So we now may compare these two equations. Comparing three and 4, what we will get? Let us see the above equations. You will find B naught equal to Q over 4 pi epsilon naught. There is no term in LHS containing B1, that is not B1 but containing 1 over R square. So here we are comparing the coefficients of 1 over R, 1 over R square, 1 over R cube. So no term in LHS is containing 1 over R square. So B1 will be equal to 0. Again B2 will be equal to what? This will be Q over 4 pi epsilon naught into A square over 2. And again B3 is equal to 0. So one thing you may see, the alternate coefficient B naught is non-zero, B1 is 0, B2 is non-zero, B3 is 0. Similarly, if you will calculate, you will find that B4 is not 0 but B5 will become 0. It means all the odd coefficients B1, B3, B5, these will vanish. In fact, after calculating these coefficients, now we can define the potential at the given point P by the use of equation 2 for the case R greater than A. So what will be our result? From 2 we have for R greater than A, R greater than phi of R theta, phi of R theta. Let us substitute all these values. This will be Q over 4 pi epsilon naught into 1 over R P naught of cos theta plus, not plus but minus, here will be negative sign, minus a square over 2r cube, a square 2r cube, P2 of cos theta, P2 of cos theta, and plus so on. In fact, this is potential at the point P, which is at a distance of r from the center of the ring and under the condition r greater than a. We have find the potential. This is a very interesting result. You have surely studied in electrostatics multiple expansion of potential. Let us see here. In first term, the factor is 1 over r, which in fact represents potential due to a monopole. In second term, the factor is 1 over r cube, and this is in fact potential due to a quadrupole. So see here, this expression gives a very important information that the potential term contains the monopole term, the quadrupole term, but not the dipole term. Dipole term contains 1 over r square. So this is another very important significance of this result. When you have studied the multiple expansion of potential, you have definitely gone through such situations. So this is a very important information which we can gather from this very problem. Now I am considering another case for which r is less than a. For r less than a. In this situation, for the finite value of r, let us see the expression for potential. When r is less than a, we can take r equal to 0. It means our limitation is 0 is less or equal to r, and this is less or equal to a. This is our limitation. So we can find the potential even at r equal to 0. When you put the value of r equal to 0 in general solution as I have stated above, you will find that when r equal to 0, then potential should be finite. But the second term, that is the containing BL over r to the power L plus 1, if in this term we will put r equal to 0, what will be the result? If you put this, the result will be in fact infinity, that is potential will become infinite. So this term must not be contained in our solution. And from this we can say, in case of r less than a, BL must be equal to 0. So in this case, BL should be equal to 0. And if BL is 0, what will be our solution? Therefore, in this case, phi of r theta, this will be simply summation L 0 to infinity AL r to the power L PL of cos theta. This will be our solution of Laplace equation when r is less than a. Now, again we find this potential in this case, that is r less than a, when theta is 0, that is we are considering the point on the axis of azimuthal symmetry, that is z axis. So for r less than a, phi at r0, as I have cleared above, what will be the potential at this point? This is in fact q over 4 pi epsilon naught into 1 over a square plus r square to the power half. But remember one thing, here r is less than a, so r over a will be less than 1. So in this case, we take out this a square as a common factor, and hence our result will be q over 4 pi epsilon naught a. And when you will take the term in denominator in numerator, what will be this? This will be 1 plus r square over a square to the power minus half. Let us again expand this by binomial expansion. We will get, after expansion, q over 4 pi epsilon naught a into what we will get, 1 minus r square over 2a square plus 3r4 over 8a4 minus so on. Let us say this is equation number 6. Now we have the potential, we have an expression for the potential at the axis of azimuthal symmetry, that is z axis. Now from this equation 5, we can define phi of r0 too. And so when we will define phi of r0 by the use of equation 5, what will be our result? Let us see here. When you will make theta 0, PL of cos theta will be PL of 1. And as I have told you in first case, that PL of 1 is equal to 1 for any value of L. So let us expand the equation number 5, taking the value of theta equal to 0 from phi of r0 equal to summation L 0 to infinity AL r to the power L and PL, as theta is 0, so cos theta will be 1. And we know this PL of 1 is what? This is in fact 1. So simply you may write this is summation L 0 to infinity AL r to the power L. Now expand it for different values of L. This will be A0 into R to the power 0, that will be simply 1, so I don't write it. A0 plus A1R plus A2 R square plus A3 R cube and plus so on. Let us say this is equation number 7. Now see, we have two expressions for the same potential. This is also phi of R0, and this expression also represents potential at R0. So we can equate or we can compare these two equations, and after comparing the different powers of R in these two equations, we can find the values of different coefficients. So comparing comparing 6 and 7. What we will get? In fact, after comparison, we will get, see the equations, A0 equal to, here A0 means R to the power 0, and in this equation 6, the terms containing R to the power 0 has the coefficient Q over 4 pi epsilon of A. So A0 will be Q over 4 pi epsilon naught A. Again, see, in equation 7 there is a term containing R, but in equation 6 there is no term containing R. It means A1 is equal to 0. Again, next term is containing R square, and in equation 6 the term containing R square will has a coefficient of minus Q divided by 4 pi epsilon naught into 2AQ. So what will be A2? Let us write, I am just writing it here. A2 is equal to what? Minus Q divided by 4 pi epsilon naught into 1 over 2AQ. So comparing the coefficients of different powers of R in above two equations, we have calculated the values of different coefficients. Now, knowing the values of these different coefficients, we can find the potential at the general point R theta, but under the condition R is less than 1. So, for R less than A, sorry, I have perhaps I have told R less than 1, but this is R less than A. So for the case R less than A, in general, what will be the potential function phi of R theta? In the light of above equation 5, you may write it, this will be Q over 4 pi epsilon naught into P naught of cos theta minus 1 over to r square over a square into P2 of cos theta P2 of cos theta and plus so on. In fact, this is potential at an arbitrary point P for which R is smaller than A. I hope from these two examples which I have solved for your convenience, you have clearly understood how we apply the solution of Laplace equation in numerical problems. This is just for your instance or for your convenience. I will suggest you to follow some standard text like Electrodynamics by Griffiths and solve such problems by taking the informations which I have dealt in this expression. Although these two examples were on regarding the problems having azimuthal symmetry, in fact, such problems containing azimuthal symmetry are very important in practice, and in different exams you will see, if you will see the papers, you will find most of the problems from this topic are asked containing the problems having azimuthal symmetry. So I have selected the problem which has azimuthal symmetry. This is all for today. We will meet together or we will interact with one another in another lecture with the solution of Laplace equation in cylindrical coordinates. Hope you will enjoy those lectures too, and have a nice day to all of you.